Imagine you have a network with two redundant data centers. So each data center would be redundant internally. It would have redundant core switches, redundant servers, redundant disk arrays. There would be a link between the two data centers so that they could exchange data. For example, if the first data center goes down, you want to have all the data already synchronized to the second data center, so that you can restart the VMs or servers or whatever it is you have in the other data center. And let's assume we actually have layer 3 connectivity between the two data centers, because if we are running the two data centers in primary backup or hot standby scenario, you don't need stretched layer 2 subnets. If you lose one data center, you already have the data on the other side, you just restart the servers, you are back in operation in a few minutes. These two data centers would, by definition, have to have different IP prefixes on the outside public LAN, here and here. Because if they would have the same IP prefix, it would be pretty hard to figure out how the traffic would have to flow into the data centers over the links connecting them to the internet. Oh, and by the way, of course, the internet connectivity is fully redundant as well. So you would have two internet edge routers in every data center. You would have two uplinks going to two different ISPs, and you would be running eBGP with the ISPs over these links. And usually the two routers on each side would have iBGP configured between themselves so that they could exchange the routes received from the service providers and ensure that the outbound traffic flows over the link that is more optimal for any particular destination. So the traffic flow between the internet and a server in one of the data centers would be pretty simple. You would have the server here and a user somewhere here. The edge routers in the data center would advertise the public IP prefix to the internet. So the traffic from the user would arrive through one of the proper uplinks, and then it would usually have to go through some sort of a stateful device, be it a firewall or load balancer or just a device doing network address translation. It doesn't matter what that device is. What matters is that device is stateful. And of course, you wouldn't want to have one device, you would want to have two devices in active-active or active standby pair, like indicated on this picture. So you would have two firewalls in one data center, two firewalls in the other data center. And so when the traffic comes in, it ends at the desired stateful device. The stateful device does whatever it does. It can be load balancing or address translation or firewalling or combination of all three of the above, and the packet arrives to the proper server. And then the return traffic goes through the same stateful device, and it usually has to go through the same device because this is the only device that has the state of this session, and arrives back to the requesting user. So with all the redundancy in place, one would say, okay, but what could possibly go wrong? So why are we even worried about the redundancy? Everything is redundant. Whatever link fails, whatever device fails, nothing bad can happen. Actually, that's not the case, because we know that when things start going badly, they go badly really quickly. You might lose this router, and you might lose this link. So data center 1 is totally isolated from the internet, even though the data center interconnect links are still up and running. So you could theoretically reach data center 1 through the internet connectivity of data center 2. If you don't believe in this scenario, if you think that two failures here can never happen, then keep in mind that these are the links that you don't control. These links might go over the same fiber that both ISPs lease from a third party, or they might end up in the same distribution box, or as someone wrote to me once, in his case, fully redundant fibers going out of the building through two different conduits, having two separate paths across the campus, eventually some were converged on a single distribution panel that was powered from a simple power strip with on-off switch and backed with no UPS. So whatever power failure would happen in this distribution panel, his data center would be disconnected from the internet, and there was nothing he could do about that. Anyway, let's assume that the failure scenario we're trying to avoid is this one. We lose all internet links, but we still have the data center interconnect in place. So data center 1 is still reachable through data center 2. Now, obviously, there are other failure scenarios to consider. For example, we could lose the data center interconnect, and then the two data centers would still be reachable from the outside world. The only problem that we would have is that we wouldn't be able to replicate data between the two data centers. What to do in that case depends on your disaster recovery policies. So are you willing to continue the operation without data replication or not? It really depends on your business requirements and your applications. So there is no good answer to this particular question. If you lose the data center interconnect link, you might decide that the two data centers can continue operating independently. Or in some cases, you might say, no, we cannot do that. And the moment you lose the data center interconnect link, you effectively take one of the data centers out of the operation. But let's get back to our scenario. We've lost all internet connectivity in data center 1. The servers are still up and running. So yes, it may make sense to start migrating the servers to data center 2, or we might say, okay, we will try to survive with some reduced functionality, particularly if the links to the internet, let's say I have 10 gig links here, and I have dark fiber here, so I have 10 gig links here on the data center interconnect as well. So in this case, I might say, okay, I could live temporarily with a situation where the traffic goes through data center 2 to the server in data center 1 and then back over the DCI link. And if the speed of the DCI link is comparable to what I had as the internet connectivity speed, then I'm okay. Obviously, if the speed of the DCI link is 1 gig and I had 10 gig going to the internet, the DCI link might become heavily congested. So this wouldn't be a good idea, and it would be better to either slowly migrate the servers to DC2 or take DC1 out of operation completely. Yet again, this is your business decision. You have to figure out what to do. And by the way, now that I started mentioning migrating servers over to the other data center, if you want to migrate the servers because the DCI link is congested, so we've lost this thing here, and now the traffic is going over DCI link, and DCI link is congested, so you want to move the servers, don't even think about doing live migration, because that will just further congest the link. So you will stop even those operations that are still being performed. So if you're in the panic mode, you don't think that you will get the internet connectivity back up in reasonable time, you want to evacuate data center 1, it makes more sense to shut down the servers in data center 1, have temporary loss of service, than trying to migrate them over the already congested link, because that will only make matters worse. But I'm digressing. So back to the original problem. We've lost the connectivity here. And now the traffic is flowing from the user to the server down here. And instead of taking this path, which is gone, now the traffic is taking this path. And you probably already see the problem in this picture. The problem is this second stateful device here, the second pair of firewalls. And there are two problems with this second pair of firewalls. First, they have no session state. They don't know what sessions were established through firewall 1. And by the way, don't even think about creating stretched VLANs and linking firewall 1 and firewall 2 in the same cluster. That's patently bad idea, so don't even think about that. And if you don't believe my short statement, please do go and read a pretty lengthy blog post I wrote about this topic. So forget about stretch firewalls. Firewall 2 has no state information about sessions going through firewall 1. That's problem number 1. Problem number 2 is firewall 2 has to perform net translations that were previously done by firewall 1, which means that whatever configuration you have on firewall 1, it has to be replicated on firewall 2, otherwise firewall 2 is not prepared to take over. And on top of everything else, you have some really nasty routing problems. Because first, the return traffic shouldn't go through firewall 1, because then it will be black holed. So you have to change the default routing so that the traffic goes over firewall 2. And also E3 and E4 have to start announcing the public prefix of data center 1. So they have to take this public prefix and start announcing it to the internet, which requires yet again some synchronization between the two data centers. And E3 and E4 have to know that this prefix is now reachable through firewall 2, whereas previously all the traffic would go through the other path. So you see, this is a total mess. Pretty hard to achieve, requires pretty complex routing setup and synchronized firewall configurations, which you know will never really happen in real life. So can we do better than that? And it turns out that we can. What we have to do is we have to create an external backbone. So we have to connect the outside routers through another link, and because we only have one set of DCI routers and DCI links here in the middle, this outside backbone has to connect to the same outside routers here and here, so that we now have an outside WAN backbone that can be used to exchange data straight between the 4 internet-facing edge routers. Now with this outside backbone in place, if we redraw the pictures and focus only on the outside side of our network, you see that we have effectively transformed our network into pretty simple, almost ISP-like network. So we have the edge routers, service providers would call them PE routers, that connect individual sites, like data center 1 here and data center 2 here. And provider edge routers also connect to the outside networks, like the ISP here, and another ISP here, another ISP here, and another ISP here. On the other hand, we have the P routers, which are our existing data center interconnect routers. And so with this outside WAN backbone, our design problems disappear all at once. Because if these links fail, then the user from the internet will see that he can still reach the public prefix of data center 1, which is now announced through E3 and E4, through these entry points, so the traffic would arrive into data center 2 and then traverse the outside WAN backbone to get to data center 1 and go through the same set of stateful devices as it did before. So regardless of what we have here, be it firewalls, load balancers, net boxes, whatever you have, because we now have the outside WAN backbone, the same stateful devices are always processing the user traffic. Also, the return routing, the outbound routing, is very simple because from every data center, you always go through the local stateful devices to reach the public DMZ, and then from there on, the edge routers take the traffic and forward it either directly into the internet if the link is available, or through the WAN backbone to the other exit point and out into the internet. So you see that all the design complexities we had on the previous picture have now disappeared with the simple introduction of the outside WAN backbone. Unfortunately, things are not as simple as they look in a pretty drawing. Effectively, what we have to do is we have to make these DCI routers be present both on the inside, because we still need some sort of secure DCI link between the two data centers, and they have to be present on the outside, the WAN backbone. The same link is used to transport both public and private traffic. So we need some sort of traffic separation mechanism. VRFs, for example, are a pretty good fit. Or, if nothing else, you could configure layer 2 transport between, let's say, this device here and this device here on the other end. So whatever you do, it makes sense to have the outside WAN backbone, and it makes sense to deploy some sort of path or traffic separation mechanism so that the outside WAN backbone and the inside DCI infrastructure use the same WAN links, but you're sure the traffic is totally separated and your security guys are happy that you're not violating any security zone boundaries. To get more information about my webinars, to register for an online session, or buy a recording or the yearly subscription, please visit my website.